Unmissable stories from around the globe, from the BBC World Service.
My happy place, this is who I am.
Search for the documentary Lives Less Ordinary and amazing sports stories wherever you get your BBC podcasts.
Welcome to The Inquiry with me, Tanya Beckett. One question, 4 expert witnesses and an answer. In October, the largest car company in the world made an announcement that sent shockwaves through the industry. Anyone who knew anything about the technology surrounding electric cars, or indeed was thinking of buying one, may well have found themselves taking note. Toyota claimed it was on the brink of being able to manufacture batteries that would power an electric car for journeys longer than 1,200 kilometres, or 700 miles. Not only that, they could be fully charged in an incredible 10 minutes. Toyota's boss, Koji Sato, cast the breakthrough as a watershed moment for car making as a whole during a high-profile announcement in Tokyo.
The commercialization of solid-state batteries is a thing of the future that is now within reach.
Changing the future of cars.
So this week we're asking, has Toyota solved the electric car battery problem?
Part 1. Batteries.
If you go really right the way back to the beginning of the automobile, there was a bit of a two-horse race between electric vehicles and combustion vehicles. It's not a new idea in that sense. Battery-powered vehicles go back right to the dawn of the automobile, but it's only really now that they've become increasingly adopted by consumers.
Over a century ago, in 1879, the American engineer Thomas Edison lit up the world with the invention for which he is most famous, the electric light bulb. What perhaps is less widely known is that some 3 decades later, in 1912, Thomas Edison went on to build 3 electric cars. If these prototype cars had gone into mass production, Thomas Edison's influence on the vehicle industry may well have changed the course of history. But by then, Edison's close friend and fellow engineer, Henry Ford, had forged ahead along another route. A few years before, Ford had already put the first affordable mass-produced car on the road, and his Model T was powered by something much simpler and more compact than a battery. It was powered by gasoline. Now, just because cars used gasoline did not mean, of course, that they didn't need batteries at all. Batteries became essential to getting the vehicle started in the first place. But in the late 20th century, automakers' environmental concerns, not to mention dwindling supplies of oil, meant they were going to have to move away from diesel and petrol. And so there was increased interest in how vehicles could be powered instead by electricity.
Hello, I'm Paul Shearing. I'm the Chair in Sustainable Energy Engineering and Director of the Zero Institute at the University of Oxford. The difference between the lead-acid battery that starts the vehicle and powers the lights and the lithium-ion battery that we find in modern electric vehicles is that the lithium-ion battery is actually responsible for the motive power, for making the car drive. So we've all had car batteries historically. That's taken care of starting the engine. Now when we've got a battery electric vehicle, it's the battery that's doing the hard work and enabling us to drive places.
The idea that vehicles could be propelled by batteries began to take hold in a commercial sense before the turn of the century. The Toyota Prius was the world's first mass-produced petrol-electric hybrid vehicle. It was launched in 1997. But it was another decade after that before the first fully electric vehicle, meaning one that didn't need gasoline at all, rolled off production lines. It was made by another Japanese car company, Nissan, and the model was called Leaf. More than 10 years later, the journey to making electric cars competitive with their gasoline counterparts is still far from complete. And the reason for that is simple.
The energy density of petrol is really spectacularly high. And so actually for many, many years, people were really trying to develop battery technologies that would become in some way competitive with the energy density that could be stored in the petrol tank to deliver the performance of an electric vehicle. And it's important to recognise that we're not there yet. For many battery chemistries, the theoretical energy density still doesn't come close to the energy density of petrol. However, it's good enough, and obviously we've seen that with the rollout of electric vehicles. The sort of modern lithium-ion batteries that we have available now can provide really quite good and often better performance than their combustion vehicle equivalents. And oftentimes the electric vehicle will outperform a combustion vehicle. So, for example, in acceleration, electric vehicles can deliver power extremely quickly.
The clear advantage of driving lithium-ion battery cars is the reduced impact on the environment. If the battery is charged with green energy, the carbon footprint is much lower than for a gasoline car. The difficulty for the driver is that, as Professor Shearing has mentioned, their low energy density means that lithium batteries need to be charged more frequently than a gasoline tank needs to be filled.
I think that in general people would like batteries to last longer. They'd obviously like them to be cheaper so we can have more mass market electric vehicles. We want to explore a range of next generation post lithium ion battery chemistries because they can fulfill a range of different criteria. They might be made from more sustainable materials. We might also see some batteries with improved safety that come into the market as well.
These are the type of problems that Toyota says it is close to fixing by swapping out the lithium-ion batteries for so-called solid-state batteries. The underlying technology is essentially the same, but the crucial difference between lithium-ion and solid-state batteries is that the electrolyte is not liquid, but solid, and this makes them more fiddly to manufacture. But the advantages they offer are so compelling that Toyota and its rivals, including Nissan, BMW and Mercedes-Benz, have spent years figuring out how to do it.
I would identify three sort of key motivations for moving towards solid-state batteries. The first is that actually for a well-engineered solid-state battery, we can probably pack more energy into the box, and that will equate for a driver as being a longer range for their electric vehicle. The second advantage is, again, for a well-engineered solid-state battery, there is a trajectory that suggests that we'll be able to charge them more quickly. And so increasing the availability of fast charging, again, is a massive bonus for the consumer. And finally, because there is the possibility of replacing some of the flammable components in a conventional lithium-ion battery with a solid material, there is also some safety benefits that we see from these next-generation solid-state batteries as well.
Is it a game changer?
It is a game changer. It's something that people have been sort of working on for now many decades, trying to get these solid state batteries to sufficient maturity to then roll out to the consumer. And the reason it's a game changer, I think, is principally because of that enhanced energy density. We could have a car that had a 500 or a 750 mile range compared to the current generation of lithium-ion batteries, which have a more limited energy density. And so in that sense, I think that solid-state batteries will be hugely enabling for the rollout of electric vehicles.
Time for our next expert witness.
Part 2. The Long Road.
Our second expert witness is Shirley Meng, Professor of Molecular Engineering at the University of Chicago.
I think solid-state batteries offer some unique characteristics that can lead to some big breakthroughs and perhaps unlock some of the applications that are previously not being able to achieve by other battery technologies.
We've already described how replacing traditional lithium-ion batteries with solid-state batteries, the type that Toyota claims it will soon be able to mass produce, has advantages in terms of how much charge they can hold. This step change is so great that in terms of driving distance, it tips an important balance in favour of electric cars.
Solid-state batteries offer the possibility to increase the volumetric energy density of the batteries. So imagine in the space of the battery pack, you can double or triple the driving range per charge that your batteries can offer. Solid-state batteries really offer this opportunity for 600 or 700 miles per charge. It's not a dream. It's actually have been calculated by scientists plus the companies like Toyota. They offered over 700 miles driving range.
But there's another important advantage. Lithium-ion batteries have often been associated with being flammable, setting on fire if they become overheated. This is due to the liquid electrolyte inside them. Solid-state batteries are able to withstand much more heat. This means that far less effort needs to be put into keeping them cool, which in turn means they aren't as heavy.
I think that one of the big example is really the possibility of you can operate your batteries at much higher temperature, let's say 70, 80, or even 100 degrees Celsius. So the thermal management aspect of the solid-state batteries will be very different from the traditional lithium-ion batteries. I think a lot of people don't realize that in electric cars, more than half of the weight is actually dedicated to do the thermal management of the battery pack.
It's not just the performance of the battery which is better, but also producing solid-state batteries is expected to be less costly both financially and in terms of the environment.
It's fascinating to think about how manufacturing processing could be innovated. And as many people didn't realize during the lithium-ion battery manufacturing process, the process is long, the steps is very tedious, and that's one of the contributing factor of high cost of lithium-ion batteries. So with solid state, we have a golden opportunity here to think about green manufacturing processes, manufacturing processes that probably use only dry process, no toxic solvent, fewer steps, because more manufacturing steps means more manpower and higher cost.
Can solid-state batteries be recycled? Are they beneficial from that point of view?
That I can say with confidence, it can absolutely be recycled. And we can learn from the pioneering experience in lead acid and the lithium-ion batteries that we must design for recycling. So when we are actually thinking about cell design, module design, and the pack design, the expertise for people who focus on circularity and design for recycling are already integrated in the team. So I think that, to me, is the other exciting things of working on solid-state batteries. And there have been quite a few publications that showcase that recycling is very promising.
Something mysterious plagues County Mayo on the west coast of Ireland and its legendary Gaelic football team.
They've come to see the game of the year.
The year is 1951, and County Mayo have just won the sport's biggest prize. But in the midst of such elation, there's a funeral, and for the priest leading the congregation, this sacrilege must be punished. A curse exits his lips. Damnation be upon every one of you. It came to pass.
Amazing sports stories from the BBC World Service. Find it wherever you get your BBC podcasts.
Time for our next expert witness.
Part 3. Toyota's Holy Grail.
Our third expert witness is a former academic and author of The Toyota Way, which chronicles the manufacturing and management systems within the Japanese car firm.
So I'm Jeff Leiker, and I was a professor of industrial engineering at University of Michigan for 35 years.
Toyota was the world's top-selling automaker in 2022, selling over 10.5 million vehicles, 2 million of which were sold in America. As we learned in part 1, Toyota was the first car company to tackle the concerns surrounding the carbon footprint of cars with the launch of the Prius. The Prius is a hybrid car, meaning the electric battery is charged when the car is running rather than from an external electric source. Toyota built it this way in part because at that time charging points were not very available. So in that sense, the Prius provided an important stepping stone.
At that time, they saw the Prius as just a segue to zero-emission vehicles and battery electric vehicles, and they wanted to have all the key technologies for an electric vehicle. And they have had them in the Prius. They also had a gas engine, so they had really like two cars in one. And then over time, they've been investing in plug-in hybrids, and they've been investing in battery electric vehicles.
Plug-in hybrids are ones that can be charged by, well, plugging them in to a source of electricity. But they can still be powered by gasoline. The reason that Toyota has been keen to hang on to gasoline engines is because drivers in the United States want to have the option of longer journeys without having to stop and wait and recharge the battery. It's a concern that Professor Leiker thinks isn't always entirely rational.
I think the average American drives about 30 or 40 miles a day. So Actually, the problem with battery electric vehicles is they have too much range for most purposes. Not that they have not enough range, but they're always worried about that one trip I take and I won't be able to find a place to plug in.
Toyota's approach is different from other car firms which have been eager to roll out fully electric cars. But Toyota argues it looks at the impact of vehicles on the environment more broadly and takes into account not just the carbon footprint from driving them, but also their manufacture.
They feel that they haven't gotten credit for how hard they believe they've worked also in the factory in reducing emissions, and they're very committed to environmental friendliness, and they've done a lot. But they've been criticized because they haven't jumped on the battery electric bandwagon wholeheartedly like other automakers. So I think that was one of the things that led them to want to go out and tell the public we've had some sort of breakthrough.
Perhaps this does offer insight as to why Toyota has been keen to trumpet its breakthrough in the area of solid-state batteries, despite remaining somewhat opaque about precisely how it has achieved it.
So even with this announcement, often when you see announcements like this, the expectation is it's going to happen overnight. But in 5 years, they'll be mass producing them, they say, and that won't be at a huge volume. So they'll put them into a few vehicles, particularly Lexus vehicles, because they're still going to be relatively expensive. I see the profile of ramping up production as something they're doing over the next 10 years, not something they're doing next year.
There is, of course, also the question of money. The cost of research in this area runs well into the billions. It's a carefully calculated but very expensive gamble.
I guess there's a risk that they would lose it all if some new technology emerged that we don't know about in batteries, but that doesn't seem very likely.
There are therefore several reasons why Toyota might take some time to get mass production underway. Money, balancing the production of solid-state batteries with demand for other technologies, smoothing out the production process, and the difficult question of getting hold of the necessary raw materials in the first place. Time for our fourth expert witness.
Part 4. Material Resources.
Dr. Evie Petavratsi is a mineral commodity specialist from the British Geological Survey, which is an independent body providing geoscientific data to the British government and other interested parties. Dr. Petavratsi is a mining engineer by training and has been working on critical raw materials for well over a decade, tracking supply chains.
The big problem is trying to extract these materials and get them to the manufacturer in the form that they need them, at the time that they need them, in the quantities that they need them.
Solid-state batteries are essentially the same technology as their lithium-ion counterparts, so they don't get around the rather concerning questions about the environmental impact of mining. The total global supply of lithium at the moment is about 130,000 tonnes annually. In the next few years, demand is expected to reach multiple times that number, mainly because of demand from the car industry.
So you're looking at increasing by fivefold the supply in the next 7 years. You know, that's really difficult to achieve. And it's difficult to achieve because to put new mines in place, it takes decades. It takes between 15 to 20 years to just produce a new mine. So how are we going to achieve that? I think there is an imbalance in the supply.
There's also the question of where battery manufacturers get their lithium from. At a time when geopolitical tensions are high and many manufacturers are looking to access raw materials closer to home, a glance at the global map of lithium production is a sobering experience. The top producers are Australia and Chile, but China has been very actively buying mines abroad and bringing the metal back home to refine it. In fact, it refines well over half of the global supply. This has led to concerns that governments in the West are getting left behind.
China is a good example where they work heavily on public-private partnerships and they subsidize exploration through that, new supplies in place. But this is not happening elsewhere. The concerning bit is that the majority of refining that happens at the moment is in China. Therefore, other countries will heavily rely on Chinese supplies. And this is where we need to see refining capacity moving outside China and expanding in other places across the globe.
Many governments in the West have already taken a keen interest in securing not just the supply of lithium, but other raw materials that their countries need for a greener future, often in the form of tax incentives. Alongside that, America has moved to limit China's access to advanced semiconductor chips used in military applications. Beijing has responded by curbing exports of some important minerals.
We have seen, especially from China, more restrictions appearing the past year or so. It started with gallium and germanium, which, again, essential components, semiconductors. And then it has moved into graphite, key component for anode materials in existing lithium-ion batteries. And, of course, it's impossible to say how these things are going to move into the future.
All this, says our expert witness, points to the recycling of existing car batteries becoming ever more important.
Looking at lithium-ion batteries that we're using already, that they come to an end of life, and making sure that the battery materials are recovered and recycled and they turn into new batteries.
Now we return to our question. Has Toyota solved the electric car battery problem? The answer is clearly that it has cracked the problem of how to manufacture solid-state batteries, which means its electric cars will now be able to travel further without needing to be recharged. The problem is the batteries will only start to be rolled out 4 years from now. Not only that, they still need lithium for manufacture, which is by no means environmentally friendly to mine, and getting hold of it has become embroiled in geopolitical tensions. But there are other battery chemistries being developed, one of which uses an element which is so abundantly available it's even to be found in our kitchen cupboards: sodium. So this journey clearly has further to run. Several car firms other than Toyota are exploring solid-state and other technologies. Professor Shearing, our first expert witness, says success will come ultimately from greater collaboration.
We really need to work together on this to deliver things at pace, because we can't procrastinate for another 20 years thinking about how to design the perfect battery. We really need to be in a position where we can co-develop batteries, roll them out in an accelerated fashion in order to have a tangible impact on the world and contribute to that decarbonisation goal.
The final word goes to Thomas Edison, the man whose ideas over a century ago to develop electric cars were parked. He died in 1931, so you'll have to hear it from me. His advice was, there is a better way to do it. Find it. This inquiry was presented by me, Tanya Beckett, produced by Bob Howard, researched by Matt Toulson, edited by Tara McDermott, and the studio manager was Gareth Jones.